Okay, so we were discussing liquefaction of soils, and in the previous class, in the last class, we discussed regarding the stress condition that develops in situ, right, and also how we can replicate that in the triaxial, and the more how the Mohr circle, the stress condition. I mean, when we plot it with the Mohr circle, how the Mohr circle moves with the development of pore pressure during the dynamic loading. Then we discussed the steady state line, all right, how that steady state line was developed and how it was arrived at, and how it can define whether a soil will liquefy or not. So we at the last part of the class, we came to the conclusion that if this is the steady state point, so the steady state point is defined by the initial void ratio, as we have seen in our previous class. So it is defined by the initial void ratio, the E value, and the initial effective confinement, so P dash. So we had a curve like this, and so this was the initial void ratio. Suppose so this is the initial void ratio. So the soils may be at different confining states, P dash, so at different confining states. So if it is above the steady state line, so we saw that when Davitric load was applied, so it moved onto the flow liquefaction, and flow liquefaction was initiated. So if the static stresses in the soil is such that it lies above this point, we arrived at this conclusion that if it lies above this point, so at any point here in this region, so it will undergo flow liquefaction during if the static stresses at the in the soil deposit at that point is more than the steady state point that it has to reach. So if a point is supposed at A, we saw that it can be liquefied in two different ways. One is through the monotonic load, and if we apply a dynamic load or a vibratory or oscillating load, right? So the shear stresses changing its direction. Once it is in this way, and the other time it is in this way. So the two stress path will plot in different ways. So if we have to apply a monotonic load, so definitely a huge amount of Davitric stress has to be applied, and it will move in this manner, right? And as soon as it reaches this point, so from this point here over here, so this was the initial state of the point, so this is the initial static stresses, shear stresses, Davitric stresses, and this was the initial effective confinement. So from this point, when we apply a monotonic Davitric load, so this amount of load is applied, additional load, so it reaches this point. As soon as it reaches this point, so flow liquefaction is initiated, and we have a stress state of the soil coming to this point. So from this point here, it comes to this point, and now there is constant rate of deformation. So constant rate of deformation at that point. And the thing is that it is stabilized at this point, so steady state point. So Q Davitric stress is stabilized, effective stress is stabilized, and there is no change in pore water pressure now. So delta U now from this point onwards. So here there is obviously there is increase in the pore water pressure. As we can see, the effective confinement moves from this point up to this point. So there is a huge amount of pore water pressure generation. So excess pore water pressure is generated as it is sheared from this point to this point. Now from this point onwards, there is a constant rate of deformation and at constant volume. So delta U, there is no change now. And the particles, they flow, they develop the flow structure which Castro 1969 defined. So the particles, they roll and they reorient themselves into a state of minimal frictional resistance state. So that is monotonic load. So the other way, so here what we did, we applied the monotonic load, and when we applied that, so stress, pore pressure was generated, and when this point was received, it was achieved. So from there onwards, there is liquefaction, flow liquefaction. Now, if there is a dynamic load, so such amount of huge amount of deviatoric stress need not be applied, so we apply a dynamic load. So in that case, so here we know P dash is equal to sigma 1 dash plus sigma 3 dash by 2, and Q is equal to sigma 1 minus sigma 3, or it may be dash. It is the same thing because pore water pressure does not affect the deviatoric stress, so divided by 2. Right? So here what happens, we can apply a dynamic load. So when we apply a dynamic load, it will follow a path of this sort. Right? Then suddenly there will be some amount of pore pressure generation and it will reach the point here on the flow liquefaction surface. So this is dynamic load, earthquake load, or cyclic triaxial load, and this is monotonic load. Right? Stress controlled triaxial. So we are applying the stress only, incremental stress. It does not decrease anymore, it is going on increasing up to this point. Okay, up to this point. Now in the dynamic load, we have applied an oscillatory deviatoric stress. All right, so it is increasing, decreasing, increasing, decreasing. So there is, as we apply the dynamic load, there is increase in the pore water pressure, and when there is increase in the pore water pressure, there is a decrease in the effective stress. So the effective stress decreases. So we know P dash is equal to P minus U, or sigma dash is equal to sigma minus U, and it moves towards the left. So as soon as it reaches this point, now there is a flow liquefaction initiating, and there is deformation up to this steady state of point. So there is a further development of pore water pressure, and from the steady state point onwards, then there is again constant deformation. So for initial void ratios, all right, and different confinements, so the steady state point will be at various positions in this uh, critical state line over here, all right, and we will have different ranges of stress condition where flow liquefaction will be initiated. So it is, if it is above this stress condition only, in this range only, so there is flow liquefaction initiated. So if, and then again, if it lies further away, so we have seen that if it lies very further away, so now Q by P dash or tau by sigma, whatever you say, that ratio is very small, and we see that we need a lot of numbers of cycle to reach up to this point, or a huge amount of deviatoric stress to come to certain point here. All right, so if the confining stress is very high, so the chances of liquefaction reduces. All right, and of course, obviously, if the void ratio of the soil is also very high, all right, if the void ratio of the soil is also very high, then also the chances of liquefaction is reduced, because here is the steady state now. So the, if for this void ratio, so it will go up, right? So there will be, in that sample there will be dilation. So if a point is here, so we saw that there is dilative behavior. If a point is here, there is dilative behavior during monotonic load. Obviously, So this is flow liquefaction. Okay, we are talking about flow liquefaction. Obviously, if the point is below this line, so now there may be chances of cyclic mobility. Okay, so what will happen is that, so suppose a point is here and the tau cyclic which we give, all right, it is not very, very significantly high. So what will happen is that, so there will be stresses here, here, and there will be development of pore water pressure, and the stress path will move in this way, this way, this way, and it will reach this point, and it will oscillate in this failure surface, and the stress condition, all right, so delta U will be 0, so stresses will be stabilized. So Q and P, so it will only oscillate between this range. All right, and of course at that point, if we apply monotonic load, so the shearing of the particle will take place in this direction. All right, it will go up. So definitely that means there is dilation in the sample. So if there is dilation in the sample, that means the positive, the pore pressure will now actually be developed, will be negative. All right, during the monotonic loading. Initially, when from here in this stage, when we apply the dynamic stress, the cyclic shear stress, so this shear stress is such that there is no reversal of shear, all right, in the sample. So there is no reversal of shear. So it is always on the same direction, all right. So it goes in this one and it stabilizes again. It goes in this side and stabilizes, all right. So in that case, there will be development of pore water pressure, and it will ultimately come and oscillate and in this failure surface. Of course, there will be some amount of shear in the shear strength or shear resistance in the soil during the oscillation as well, but there will be huge amount of deformation. All right. So because the effective stresses has considerably reduced. So that is one case. In if the cyclic shear stress is such that it somehow reaches the flow liquefaction surface, all right, then momentarily when it will again cross the flow liquefaction surface, all right, so there will be a state of liquefaction, momentary state of liquefaction, all right, and in that momentary periods significant amount of shear strains will develop, and there will be, if the static stresses are such that it is still, acting on the soil deposit, so significant amount of deformation may be occurring. So such as lateral spread, all right, or maybe some slope stability failure. So those kind of things may happen, all right. Then again, if the shear stresses is such that if the shear stresses is such that it changes direction in this manner, all right, so there will be huge amount of pore water pressure generation during the cyclic loading. So it will very quickly move to this state over here, and the failure line will be in this manner here, all right, and the stress state in the soil will now oscillate between this range over here. So you can see that it moves to this point and again to the other side, again it comes to this point, again to the other side. So this point here, if you consider here, so this is a point where effective stresses are 0. So this is a point where the effective stresses are 0. So this is basically the, it is same as the initial liquefaction state, all right, which we discussed in our in the triaxial cyclic triaxial test that we discussed in our previous class. So same, the initial liquefaction, as we saw that the Mohr circle moved to the left and it came to this point and there was huge strain in the sample developed. So it is in the initial liquefaction state, all right, and therefore there is significant amount of straining. Now if again from this state also, if we apply monotonic shearing, so instead of dynamic load, instead of this oscillating load, now if we apply a constantly increasing shear stress, what will happen is that the particle, the stress state will move along this failure surface, right, along this failure surface, and it will come to this steady state, and there will be ultimately again dilative behavior. So pore pressure again will become negative. So there will be increase in the effective stress, as we see. So increase in the effective stress again. So now the soil will actually stabilize, all right, and the shear stress required to cause deformation in the soil will increase with the deformation in the soil. So the soil will actually, you cannot cause, constant deformation in the soil as the shearing will continue, shear strain will continue. Also, you have to go on increasing the deviatoric stress or the shear stress in the soil. So only then only you can cause deformation now in this state, all right. So obviously that is not the case. So if the stress state is below this range, we have cyclic mobility, and we have seen how the various cases of cyclic mobility may be induced in the soil. All right. So considering summarizing all the tests that has been done, so we can pick out some of the main factor or main criteria which actually is very important as far as liquefaction is considered. So one is obviously the peak deviatoric stress. So that is the tau cyclic, as you say, all right, or Q. So that is the peak deviatoric stress. So with peak deviatoric stress, peak pulsating stress, so we see that numbers of cycle reduces. So if the sample is sheared, it is given huge amount of shear, and this is changing its direction. So as we have discussed in this case here, right, so this is the case. So we see that the numbers of cycle required to cause liquefaction, it reduces, all right, as pulsating stress increases, numbers of cycle reduces. Alternatively, as pulsating stress decreases, we need more numbers of cycle to cause the liquefaction. Obviously, it was here also I showed that if the shear stress is more, it will reach quicker. If it is less, more numbers of cycle to reach the same state. So that is what is happening here. All right. So this is for simple shear test. This is for simple shear test, and this is for triaxial test. Obviously, in all of the tests, the same pattern was observed. All right. So higher stress, cyclic stress, less numbers of cycle. So it is correlated to the, we can correlate it with the peak acceleration. All right. So when we use the acceleration coefficient, so kv, all right, and kh into g, all right. So the coefficient of horizontal acceleration, coefficient of vertical acceleration, all right, or maximum acceleration. So alpha g that we use, so 0.1 times g, 0.3 times 36 g that we use in our design. So these are some design acceleration. So as you see, peak pulsating stress is it is similar to the peak acceleration. So ultimately, it is the stress, you can say, is equal to mass into acceleration. Okay, so if the acceleration is more, the cyclic stress is also more. So with increasing amount of acceleration, there is increasing amount of pore pressure generation. Right. So acceleration, more acceleration, quicker liquefaction. So that is the case. Then of course the relative density, as we have seen, the void ratio is an important parameter. So with decreasing void ratio, we see that the steady state will go up. All right. So of course there is chances of cyclic mobility now. There is no doubt about that. But the initiation of flow liquefaction is reduced, and therefore, and also not only that, with increase in the initial relative density, the shear strain that it will cause. So if you again consider that case of steady state case, so here we have the flow surface. So if it is, suppose we have a cyclic mobility here, so we have reached a cyclic, we have reached a state of initial liquefaction here. So from there, if we apply even monotonic load, so there will be dilative behavior. Right, so there will be dilative behavior. So in that case also, my pore water pressure will be negative. Right, so here we see, so initial liquefaction, so this is a dense sand. All right, so concentrate on these two curves now. So this is a loose sand and this is a dense sand. So in the loose sand, as soon as there is initial liquefaction achieved, suddenly, so if I draw the axial strain curve, so it is here, no strain, no strain, no strain, then suddenly there is huge amount of strain. So you can see it is very close, 20% strain has already achieved, right? So numbers of cycle for same numbers, or in 2-3 cycles itself, it is already, it is the deformation is uncontrollable, right? So it is going haywards. But when there is the relative density is high, so it is almost 100, so it is totally compacted sand, so you can see that. So initial liquefaction we have achieved here. All right, it is almost comparable. Of course, the pulsating stress is significantly high, but numbers of cycles are almost comparable. But the pulsating stress is high. You can note that, right? So here initial liquefaction is achieved. So if I draw the axial strain now, so here we have achieved initial liquefaction. So now the state is that P dash is equal to 0. But what is happening is that to achieve 20% strain, all right, so you can see how many numbers of cycles are required. So it will go on slowly, increasing, and like that. Okay, so that is the effect of initial relative density. Obviously, if we now stop the cyclic loading and we apply monotonic loading, definitely the soil will, with shearing, the shear resistance also will increase, and you need significant amount of deviator stress, which is, that means the soil will ultimately be stabilized. All right, so that is the effect of initial relative density. So here you see pore pressure generation as well. So with increase in relative density, there is lesser amount of pore pressure generation. Right, the pore pressure generation reduces with increase in relative density. So definitely, if the pore pressure, generation is less, definitely we will have a, more numbers of cycles will be required to achieve the state of liquefaction, initial liquefaction. So here we see, so this is peak pulsating stress. So this is tau cyclic, that means, all right. So with increasing relative density, so for the same confinement, so we have, so for the 100 cycles, so this is numbers of cycles is 100. right? So I mean this I mean considering the numbers of cycle constant, that is 100 cycle. So the peak pulsating stress, so here you see that it is increasing asymptotically, right? So here also same behavior at the various confinement, same behavior. Again with increasing confinement, higher pulsating stresses required. Obviously, if you see here that stress condition is that ratio is very significant as well, right? So here with increasing confining stress, we need higher pulsating stress, right? So that is means the Davidic stress or the shear stress, cyclic, tau cyclic, right? And with increasing density, we need higher cyclic stress to cause same, I mean to arrive at the same amount of same state, same liquefaction state with increasing density, right? With increasing density also the cyclic ratio, I mean cyclic stress has to increase. So obviously you can see here, so this is for loose state, all right? So this is for loose state and this is for dense state. So for dense state you can see there is significant amount of increase in the cyclic stress or the pulsating stress, and whereas for the loose sand not that much amount of increase in the stress is required. But then again the behavior, right? So with uh, increasing confining stress, now okay, so this is confining pressure, okay, so this is now the effect of confining pressure. So P dash or sigma 3 sigma C dash or sigma 3 dash, whatever you say, all right? So confining stress. So with confining stress, so you see numbers of cycle we have to go on increasing, all right? So pulsating stress, if it is less, so let us consider this case. So this is sigma 3 is 1450 kp. So we are here, so from here the pulsating stress has to be increased to decrease the number of cycles, obviously that we have already discussed. Then for increasing confining stress, so same trend is observed but it is increasing, all right? So the shear stress, pulsating stress is also increasing, as well as, so the pulsating stress is also increasing, as well as the number of cycles is also increasing. So that is the effect of confining pressure. So we have already discussed in detail when we have looked into the, we have discussed in the steady state line. So the effect of confinement we have already taken into consideration. So how the soil will when the soil will be, when there will be flow liquefaction and when there will be cyclic mobility, right? So same case here also it is observed in case of dense sand also, but it is more, the I mean the trend is almost same, but the values and the magnitude is significantly high. So higher numbers of cycle and higher pulsating stresses are required for increase in confining stress. So the same here you see for the same trend is observed for simple shear test results as well as for the triaxial test results. Obviously for the triaxial test results, uh, we have a higher values of this pulsating stresses, with the ratio is a little bit high on the higher side. And here you see for increasing confinement, so this is increasing confinement here, so the same trend is observed, right? And in the simple shear it is same trend is observed. Of course simple shear it is directly sheared, so the stress ratios are a little bit on the lower side. So this is numbers of cycle increasing with pulsating stress decreasing, And for increasing confinement, we have an increase in the pulsating stress as well as an increase in the numbers of cycle. Now if we plot that, all right, so that we will get we will get a linear actually relationship between the initial effective confinement in the sample and the peak pulsating stress. All right, so the peak pulsating stress and the initial confinement, we have a linear relationship for various numbers of cycles. So this is 10 numbers of cycle. So if we consider 50 numbers of cycle, it will be somewhere here like this. Okay, so 10 numbers of cycle if we consider, and we plot the initial effective confinement and the peak pulsating stress. All right, so to arrive at the initial liquefaction state, so we have a linear behavior. So increase in effective confinement stress, we need to increase the pulsating stress as well. So this is the stress ratio. This is the stress ratio required to cause liquefaction in the initial liquefaction in the soil. All right, and for 100 numbers of cycle, you can see the stress ratio, it decreases. All right, so the proportion of the stress, the rise in the cyclic stress, it reduces compared to the confining. So lesser peak stress is required in the 100 numbers of cycle. That is obvious, of course obvious. Right? Now this is a very important graph. So this particular test was done in a shake table test. All right, so vibration in a model test. So this was a model test result. So with surcharge load given on top to increase the confining pressure, right? So here you see beyond a particular confinement, so the effective overburden actually aided in stabilizing the soil. Right? So what is liquefaction? So delta U, excess pore water pressure, has to be equal to the initial effective confinement. So that means if I say sigma dash is equal to sigma minus U, so now plus delta U. So if this has to be equal to 0, so we have sigma dash is equal to the increase in the pore water pressure, that is delta U. So that is why it is 45 degrees. So this is the line of liquefaction. So this is the line of liquefaction. So if there is increase in the pore water pressure, excess pore water pressure, if there is increase in the excess pore water pressure sufficiently high enough, higher than the initial effective confinement, all right, initial effective overburden pressure, here it is mentioned here, so then there will be liquefaction. So here in the lower regions, what happened, there was significantly the excess pore water pressure developed, so that it went up, it actually went up. So this is a region of zone of liquefaction. So this is a zone of liquefaction here. Then from a particular point again there was, and in fact after a certain state we see that the pore water pressure is, the development in the excess pore water pressure is in fact negligible, and there is no chances of liquefaction whatsoever. Right? So there is only in the lower confining pressures, right, in a certain range of pore water, effective confinement, that there is chances of liquefaction. In fact, this also correlates well with the flow liquefaction surface. So here, all right, so we have, if the particle is, if the soil sample is in this stress state in the field, and it is closer, as it is closer to the flow liquefaction surface, it is more prone to liquefaction. All right, so lower confining stress, towards the lower confining stress. If it is at a higher confining stress, it is further away from the surface, and therefore we need, of course it is, here in this case as it is shown, it is almost uh, non-susceptible to liquefaction. So summarizing from the various test results, so here we see for the triaxial test results. So this is the triaxial test results, and this is a simple shear test results. So obviously in the simple shear, since it is directly, the sample is directly shear, and high amount of shear is actually applied to the sample. So here what happens, so the peak pulsating shear stress, so here we see that the values are on the lower side from obtained as from the simple shear test results. So for 10 numbers of cycle, initial effective confinement to the peak pulsating stress, we have this relation. So for 10 numbers of cycle, so high pulsating stress is required. I mean higher, a little bit comparatively higher. Then for numbers of cycle, as it goes on increasing, we have other lower. So in between these 10 numbers of cycle and 100 numbers of cycle, whatever values is there, it is in this manner only. Right? So pulsating stress and initial effective confinement. Similarly, for the triaxial test results also it was obtained. Obviously, for numbers of cycle, it was, I mean, the difference was not as case in simple shear, but here also a similar trend was observed. So with increasing in confining stress, we have an increasing the stress ratio, the I mean the pulsating stress that is required, right? And in fact, so 10 numbers of cycle and 100 numbers of cycle, so everything in lies in between. So this is a summarized I mean plot of all the tests which has been done. So effect of numbers of cycles we have already seen. So here another thing to note is the effect of relative density as well. All right. So here we see two confining pressures. So one is low. So this dotted line is low, and the dark line, it is on the higher side. Okay. So here we see for the 50% uh, relative density, so it is almost closer to each other. Of course, for numbers of cycle increasing, decrease in pulsating shear stress or cyclic shear stress. With cyclic shear stress increasing, there is decrease in the numbers of cycle. Right. Same trend for all density, but again now let us concentrate on the 80%. So the gap between the two has increased. Now if we consider the 90, it is significantly more than the 50 atm, similarly in the 90. So confining pressure and relative density. All right. So with relative density, you can see lower relative density, less amount of cyclic stress for the same numbers of so if we consider hundreds numbers of cycle, so for the same number of cycle, less amount of cyclic stress for the lower density, higher cyclic stress for the relatively, so I mean high relative density. Again for confining stresses, so for the confining stresses with increasing confining stress, so higher I mean this cyclic shear stress. Then with the relative density, you can see with increasing relative density, again for same numbers of cycle, higher I mean this cyclic shear stress. And of course the effect of the confining pressure is actually more, the effect of the confining pressure is actually more as the relative density also increases. So that is the effect of the relative density on the initiation of the liquefaction. Okay. So this is a summarized test result. So here what is been done is that the y-axis has been presented in terms of the stress ratio. So tau h by sigma phi. It has been presented in the stress ratio. So tau h is the horizontal and the sigma phi. Right? So in simple, in simple shear, what was done. Okay. And we can see, so this is the numbers of cycle increasing, and we have a very similar trend. We can say it is a very similar trend for all various relative densities. All right. So with increasing relative density, it is increasing in this manner. Of course, again with OCR also we can say the same thing. So with increasing OCR over consolidation ratio, that means the soil is being consolidated, so the void ratio is less, all right, and all the relative density is high, right, whatever way you say. So with OCR, increasing OCR means the soil is consolidated. So definitely with increasing OCR we need higher stress ratio for the same numbers of cycle. For 10 numbers of cycle we need higher stress ratio, right? Again, similar trend is observed for the different OCRs, all right, different over consolidation ratios. For similar trend in the cyclic stress ratio to the numbers of cycle is observed. So almost similar behavior to this one as well, all right. Now this is a important plot. So here three sands were taken. Three sands were taken. So this is the Ukai sand, this is the Obra sand, and this is the Tenukhat sand. Tenukhat sand. So observing the pore pressure and the acceleration. So this is the acceleration versus the pore pressure. So observing the acceleration versus pore pressure, we can definitely come to the conclusion that Ukai sand is the most coarse. Right, so the particles are big. Then we can say it is the Obra sand. So the Obra sand is in between, and then we can come to the Tenukhat sand. So it is, the particle sizes are small. Right, so it is finer than the Ukai sand. Of course, how fine, that is, I leave it to you. You can go and study that in detail. Another important part of this study is the dissipation of pore water pressure. Right, so with increasing coarseness, you can see the Ukai sand, whatever pore pressure was developed, suddenly quicker than the other sands, it got dissipated, followed by the Obra sand and followed by the Tenukhat sand. So obviously we know if the soil is coarse, so it is almost proportional to the grain. The grain size is size of grain size is proportional to the permeability. So if it is coarse, so higher hydraulic conductivity. All right, so bigger pore size. If the sand is coarse and uniform, of course, obviously there are bigger pore size, bigger, larger size pores, and the pore water pressure, whatever it is generated, it can escape quicker than the finer sands. Right, so that is what was observed in the Niigata as well. So in case of Niigata earthquake, as we have studied in 1964. So there the researchers, they did a grain size analysis of the Niagara sand that were liquefied, and it showed that it was almost in the range of fine to medium. So you can see it is almost in this range. So it is fine sand, and medium sand. So mostly fine sand and medium sand. So they were the most prone to liquefaction. All right. So Sulani sand actually had a higher amount of fine content. All right. So we will check afterwards whether Solani sand was liquefied or not. But Niigata sand, you can see the Niigata main emphasis is on the Niigata sand here. So we have the Niigata sand here. So this is the plot. So it ranges from here to here. So obviously you can see majority of the fraction of the soil is actually in the medium sand and the fine sand. All right, and Ukai sand, you can see Ukai sand. This is the Ukai sand. Right, so significantly coarse sand, and therefore whatever pore pressure was generated, quickly it got dissipated. Right, then we have the Obra sand. So this is the Obra sand. So this is the Obra sand. So this is the Obra sand, followed by the Obra sand here. Then we have the Tenugat sand. Now compared to Ukai, Obra and Tenugat sand, the Niigata sand is also very much uniformly distributed. The grain size is uniformly distributed. All right, that means it is almost composed of entirely of medium and fine sand. So uniform. Gradation is uniform. All right. So that is also a important factor, important criteria for liquefaction of soils. So we can summarize the factors, various factors. What are the various factors for liquefaction? Obviously, the peak pulsating stress, which we have found out, and it is correlated to the ground acceleration. All right. So earthquake acceleration, what is the Amax? So peak ground acceleration, so peak pulsating stress. So that is the first criteria that we can isolate. Then, of course, the numbers of cycles. So we have seen if tau h is less also, if there are higher numbers of cycle, so the soil may get liquefied. Of course, if the cyclic stress is more, than so many numbers of cycles of pulsating stress is not required, and within maybe 10 or 15 numbers of cycle it will be liquefied. Then of course the confining stress or the confining pressure. So we have studied that if it is at a high confining pressure, if it is at a very significantly high confining pressure, obviously there is very low chances of liquefaction. It's only when it is on this side in this range, so there is also chances of cyclic mobility as well as chances of flow liquefaction as well. Right, then obviously the relative density or the void ratio or whatever way you say that, in fact both of these two are almost similar to each other. So with higher relative density, we saw with higher relative density the requirement of numbers of cycle as well as the peak pulsating stress increased. So this is increasing relative density or increasing over consolidation ratio. Same trend was observed in both the cases. So these are some of the criterion of liquefactions of soil that we can isolate, and we can these are the max. They are the main factor that governs the liquefaction of soil. So other than that, we saw that grain size distribution, right? If The soil is in between medium, so Niigata sand we saw in between medium and fine sand. All right, and then if it is uniformly graded, so very prone to liquefaction. All right, then of course relative density, critical void ratio we have already discussed. So particle shape is also another case. So if the soils are very angular in nature, all right, so if they are angular in nature, so definitely there will be more amount of friction. All right, so the internal friction will be somewhat high, all right, and the shear resistance of the soil will be more compared to the rounded particles. All right, so the rounded particles will easily roll over each other, and there will be it will be easy to uh, liquefy or easy to deform during cyclic stress application. Then we saw the drainage condition. If the pore water, if all liquefaction phenomena is ultimately governed by the generation of excess pore water pressure. If the excess pore water pressure can be dissipated quickly, very quick, in fact, if it can be dissipated instantaneously as it is generated, it is dissipated, there is flow, so there will be definitely settlement in the soil, no doubt, settlement will be there, but liquefaction will not be occurring. All right, in fact cyclic mobility also will not occur if it is so quickly dissipated. So ultimately drainage condition is one factor. In fact, when we will study the various methods of uh, I mean liquefaction mitigation, all right, so we will see that these are the only conditions, this liquefaction condition, then the void ratio or the relative density. So if we increase the relative density, if we vibrate the soil, if we compact the soil, all right, so the relative density will increase and the soil will be less prone to liquefaction. If we increase the drainage condition, if we install some drainage paths in the soil, all right, PVDs in the soil, then obviously the pore pressure generated will be quickly dissipated through the the drains. As soon as it is dissipated, definitely there will be settlement in the soil, but the liquefaction condition will not develop. Of course, the confining pressure also we discussed in detail. Peak pulsating stress we have discussed. Numbers of cycle we have discussed. Over consolidation ratio we have discussed. Aging and cementation is related to the over consolidation ratio. In fact, depositional environment. So here we have seen in the flow liquefaction surface that we have developed. So if the stress state in the soil is somewhere here, all right, somewhere here, so there is chances of cyclic mobility, but at least there is no chance of flow liquefaction. So the depositional environment, it is very I mean critical. So whether also we have seen that the void ratio, when it is isotropically consolidated, it is on the higher side. If it is not consolidated, it is on the lower side. All right. So depositional environment has effect on the relative density, the void ratio, as well as the stress state in the soil, and of course the superimposed load. So this is same as it can be correlated to the confining pressure as well. Of course, if the superimposed loads create deviatoric loads, create deviatoric stresses, then of course, so if the stress state in the soil was here, and then I constructed this building, all right, and then it suddenly moved up to here. So now it is closer to liquefaction, occurrence. All right, it is more, there is more chances, it is more susceptible to liquefaction. So that is also one case. So superimposed loads can act in both ways. So if the confining pressures are increased due to the superimposed loads, so it will the confining pressures will increase, so it will go in this direction. All right, so the chances of liquefaction will be reduced. So these are the criteria for liquefaction. So some brief criteria, some important points of thumb rules were given by the various standards. So it can be summarized. to few points. So one is of course shallow depth of groundwater table, obviously. All right, so the groundwater table has to be at a shallow depth. So if it is found as a thumb rule, if it is found that if the groundwater table is below 10 meter, then there is very unlikely chances of, there are, it is not likely that there will be liquefaction. All right, and up to 20 meter, if the soil is in a partially saturated state, up to 20 meter, if the soil is in a partially saturated state, all right, then obviously there is no chances of liquefaction. So this is a thumb rule. All right, then we see for grain size. All right, so if the 50% finer is less than 10 mm and 10% finer is less than 1 mm, there is chance of liquefaction. All right, so that is one criteria for the grain size analysis. Then the fine contents. Right? If it is less than 36%, fine contents means 75 micron, which we use. Actually, here fine contents means the clay size, all right, 2 micron, I think. All right, so 2 micron. So if the soil is, that means if the soil is cohesive mainly, all right, so we can see if the soil is cohesive. So here what we can say is, so we know uh, shear strength of soil is given by C dash plus, or C, in fact we can write only C, that is the cohesion, plus effective normal stress into tan of angle of internal friction, effective angle of internal friction. So if there is some amount of cohesion in the soil, so even if this becomes 0, so ultimately the shear strength in the soil remains. All right, so this is basically what happens in the cohesive soil. So cohesive, of course, there may be quick clay condition or there may be partial loss of shear strength. There may be deformation, but this flow liquefaction state, all right, may not be totally achieved, right? And the soil may stabilize. So this remaining shear strength, that is the cohesion in the soil, will help in stabilizing the soil, will help in uh, reversing the chances of liquefaction in the soil. Now, so these are all the criteria. So from the tests that we have done, so we can identify some criterion based on the stress ratio. Right? So seed and peacock, so seed and peacock, what he did, uh, he related the ratio of the, so in the field, if you remember, so we had one element in the field, all right, and then we had the base rock. So in the base rock we applied the earthquake motion, and the earthquake motion, it traveled as a shear stress wave, all right, up to the element. So basically the element is now being given a horizontal shear stress, and we have the vertical shear stress, normal stress on the soil sample. So Seed and Peacock 1971, all right, Seed and Peacock 1971. So they defined certain condition, certain stress ratio. All right. So they defined a stress ratio to establish the criterion for liquefaction based on the stress state of the soil. All right. Based on the stress state of the soil, they wanted to establish the liquefaction criterion. All right. So obviously here what they defined is, first of all, for the field liquefaction state, so they define the ratio as shear stress in the horizontal direction by the vertical stress. All right. Now, in case of simple shear, so this holds. All right. So, in case of simple shear, it is tau by the normal stress. All right. Or the in case of simple shear as well, it is the same thing. So we can write tau v by sigma v. So simple shear, if you have remembered, so we have this plates over here, and it deformed in this manner, and we have the sigma v here, and we have the tau h here. All right. So this is one stress ratio. All right. And the other stress ratio for the triaxial, cyclic triaxial is, if you remember, it is sigma d by 2. All right. So if you remember the Mohr circle, so we had a total of sigma d deviator. All right. And this is the sigma d by 2, and this point is the sigma 3, the mean constant mean, and the maximum extreme principal stresses concept that we have. So this is another ratio that we can define. Okay. So we have to understand the various stress state in the soil, the relative density, all right, and the void ratio and the stress state, and all of these criteria working with each other together, the interaction of all of these criteria together, to understand whether soil will liquefy or not, whether there will be liquefaction, initial liquefaction initiated, whether there will be liquefaction initiated in the soil or not. So seed and peacock, so they defined a ratio. So the first ratio that they defined was the shear stress developed, or the peak change in the shear stress during cyclic loading, all right, to the normal effective stress. So that is the first criteria. In fact, first and the second criteria, they almost are the similar, so I have clubbed them together. So what he did is, he from the simple shear, what he got, that is tau h by k naught sigma v. All right. So he equated it to the sigma d by 2 by sigma 3. So he equated the simple shear condition and the triaxial shear condition. And ultimately what he found was, came to the conclusion was that, so this ratio sigma v, so in case of the triaxial test, we need to multiply the k naught factor, right, sigma d by 3. So this is the first and also the second criteria for the stress condition for criterion for liquefaction of soil. All right. So if this, so this is the stress ratio that he defined. All right. Then, so in the third case, what he did was, so if you remember, we have the Mohr circle. All right, and this is the mean and this is the maximum stress. All right, so he defined a ratio, stress ratio of the maximum shear stress. So this is the maximum shear stress induced during cyclic loading to the mean effective stress, All right. Now let us consider the sample in situ. So we have the sample in situ. All right, we have the sample in situ. So we have the sigma v, and obviously we have k naught sigma v, and in this direction, and in the other direction the same value k naught sigma v. All right, so this is the three-dimensional case, actual case in the in situ condition. All right, so if I have to find out the mean principal stress, so as we have already uh, studied, so it is sigma 1 plus sigma 2 plus sigma 3 divided by 3. So here it is sigma v plus k naught sigma v plus k naught sigma v divided by 3. Right, and in case of shear stress, all right, so here we have the shear stress, that is the maximum cyclic stress, which is given by tau h square plus it will be half of sigma v into 1 minus k naught whole square. Okay, so that is the tau cyclic. So he defined the ratio of these two stresses. All right, of these two stresses, ultimately what he did is, again he came up to the ratio of tau h by sigma v. Okay, so tau h by sigma v. So he gave he did a mathematical deduction of all of this, and he came up to a significantly long equation. All right, and that is for your case, it is for you to do self-study. All right, then, so this is the basic criteria, means, all right, so we have a tau cyclic, so this is the maximum cyclic stress, and so this is tau h. All right, so this is the shear stress which is induced in the element, and we have the sigma v and k naught sigma v, horizontal and horizontal in the two direction. So we have the mean stress and we have the shear stress, and ultimately we have to find out the ratio of shear stresses to the vertical stress. So that is the second, this is actually the third criteria given by Seed and Peacock. Right, the first and second are almost similar, and therefore I have clubbed it together. So that is defined by the k naught. Ultimately here also you have to find out in terms of confining stress. All right, and ultimately the value of k naught you have to find it out. All right. Now Same thing was given by Castro in 1975. So in 1975, what Castro did was, he, instead of defining it in terms of the normal stresses and vertical stresses and shear stresses, what he did was, he used the stress invariance. All right. In fact, octahedral normal stress, octahedral normal stress is same as the mean stress, if you see. All right. So we can write sigma octahedral, effective sigma octahedral is equal to sigma 1 dash plus sigma 2 dash plus sigma 3 dash by 3. So ultimately it is equal to the effective mean. All right. And we have already studied about the Davidric stress as well. So we know Q. So in Cambridge notation that we have studied in our previous classes. So in the Cambridge notation, so we define it as Q. So Q is equal to 1 by root 2. All right. So sigma 1 minus sigma, minus sigma 2 whole square plus sigma 2 minus sigma 3 whole square plus sigma 3 minus sigma 1 whole square. Now in case of tau octahedral, it is 1/3 of this value. Okay. So ultimately what he did, he defined the term for the simple shear case and for the triaxial this case. All right. And he for the triaxial case, so for the triaxial case we have sigma 1 and sigma 3. All right. And for the simple shear we have tau and sigma n, all right, or sigma v. And ultimately what he did is, he correlated the ratio of the two. So tau octahedral by sigma dash octahedral for both the cases. So for simple shear is equal to tau octahedral by sigma dash octahedral for triaxial case. All right. And ultimately he deduced a stress, coefficient of this correlation, a coefficient of correlation, and that is how he defined the stress ratio for the stress ratio for criterion for liquefaction. All right. So ultimately he defined a stress ratio for alpha, so that is alpha. All right. And alpha is equal to 2/3 of 1 plus twice k naught by root of 3. Okay. So ultimately simple shear, we have to correlate to triaxial test, and we have to find out what are the ratios that required for correction. Okay. So based on those analysis, so some correction factors were given. All right. And it was observed that actually for simple shear condition, the laboratory estimates of the cyclic stress ratio was significantly high, a little bit higher. All right. So it was a little bit higher than in the field. So in the field, so to correlate the two, all right, that is to correlate the the results from the simple shear to the field condition. So a correction factor was given, which is beta, and similarly for the triaxial condition also a correction was given, which is called the CR. All right. So ultimately tau h by sigma v in the field is equal to beta into tau h by sigma v. It will be for the simple shear, right? So this is for the simple shear. Again, for triaxial case, same thing, alpha dash into beta, as we have in the previous slides we have seen, alpha dash into beta sigma d by 2 by the confining stress, that is the sigma 3. So this is for triaxial case. Okay, or we can directly correlate this to the CR. So this is CR sigma d by 2 by sigma 3. Okay, so now in the laboratory what we have to do is, in the laboratory definitely we will do the test for our the relative density that we have thought of. All right, we have already assumed that we will do the test in this is relative density, and we will come up with various curves. Now how to correlate that with the field? In the field you will find with different relative density. So definitely what we can do is we can correlate the two, and we can interpolate the two easily. Okay, so uh, for the simple shear case we can do use this correlation direct, this trans interpolation, and for the triaxial case we can use this correlation, right? So you can see it is in fact we have seen there, we have seen a relative linear to the effective confinement and the pulsating stress and this numbers of cycle. All right, so we have found a relative, this one linear, and here also similarly we see that there is a linear relation to the relative density for the various pulsating stress. All right, or the stress ratios. All right, horizontal stress to the vertical stress ratio, shear stress to the vertical stress ratio, tau h by sigma v, and this is the numbers of cycle. All right, so for different relative density we can interpolate. So from the summary of the laboratory test we come up into two different mechanism of liquefaction. One is entirely the flow liquefaction. So the initial static equilibrium, whatever was in the state, the stress strain history that it collected, the loading condition, and the soil fabric that got developed, the soil structure, the consolidation states. All right, what was developed, all of that are totally obscured. All right, all of that are lost. So it is totally destroyed means. And the steady state strength or the residual strength, so in different books you will find different versions of the same parameter, is only the remaining shear strength or the shear resistance of the soil, liquefied soil, and ultimately only two criteria remain, that is the void ratio and the effective confinement. So all other parameters are lost in the flow liquefaction, and there is the flow structure developed. So in fact we have discussed all of this in detail, so this is just a summary. Now in the cyclic mobility what we have observed, so liquefaction state is triggered by cyclic loading. All right, so there has to be loading, cyclic loading, and the static shear stresses in the soil deposit is lower than the shear resistance, so there is only incremental deformation. So static shear stresses are lower in the soil deposit. So we saw that in the flow liquefaction surface. So this is the steady state strength, and the static stresses are actually at the lower state than the shear resistance in the soil. So incremental deformation when cyclic shear. So we saw that when it reaches this state, so there is incremental deformation. All right, we have discussed that in detail in the previous slides. Then so now assessment of in situ condition. So all of this it is very necessary to evaluate the liquefaction potential. All right, all of this state we have to intricately, very thoroughly we have to assess to evaluate whether the soil will liquefy or not. So summarizing all this, D'Alba, Sear and Chan in 1976, so they came up with certain uh, I mean uh, I mean thumb rules. All right, so to say, so they came up with certain thumb rules. All right, so they did tests for various relative densities, so various relative densities, and they plotted the stress ratios. They plotted the stress ratios to the numbers of cycle for various strains. So you can see with increasing strain, so with increasing numbers of cycle, so there is increase in the strain as well. So this is 5%, 10%. So this is 5%, 10%, 15%, 20%, in fact 25% for the relative density of 54%. All right, similarly 5%, 10%, these are strain. All right, so if we draw this, so up to a certain point there is no strain, then suddenly there is strain. So what is the percentage of axial strain? So this strain here, so that is the 5%, 10%, 15%, and in fact again for relative density 90%. All right, so this is the 5%. So they plotted the correlations of all of this. All right, and they found out that for low relative densities there was initiation of liquefaction and suddenly it shoot up and then it got stabilized. All right, then it got stabilized. So they plotted all of this values for various densities and they came up with this curve. So we can see with increasing relative density the limited shear strain in the soil, it is decreasing. All right, and they came up with the idea that beyond 45% relative density, as soon as it reaches initial liquefaction, so there is uncontrolled uncontrolled what to say, like strain. All right, and there is unlimited shear strain. All right, so that is what they came up with, and they plotted the various stress ratios for various relative densities, and you can see for different various strains. All right, for various strains, so these are the strains limit. So stress is 10 numbers of cycle. All right, and with increasing relative density you can see that the strains is significantly decreasing, and also the distance. All right, the distance. So here you can see the distance it is. So here the 25% strain is achieved here itself for the density of 50% maybe. All right, suddenly there is high amount of straining. All right, shear strain. So that is what they came up with. So that means for low relative density soil, when there is liquefaction, as soon as there is liquefaction, there is significant amount of strain. Whereas for high relative density soil, for compacted sand, although there will be liquefaction, though there will be a liquefaction, there will be small amount of strain, and that strain may not cause significant stress to the structure which is built upon that, but ultimately there will be liquefaction. Okay, but we have to see whether that liquefaction will be enough to cause settlement or tilting of the structure on the top of the uh, soil strata. All right, so To do that, we have to do the evaluation of liquefaction potential. So how to do the evaluation of liquefaction potential? So basically what we do is we first of all find out what is the cyclic stress in the soil. So we can easily say it is mass or density into acceleration. Alright, so gamma h by g, actually mass, alright, we can say mass per unit area, suppose per unit area. So gamma g by gamma h by z, so that is mass. So gamma, suppose we have at this point, so this is h. So for a unit area, so the volume of this entire soil on top, all right, so that soil is accelerating in this direction and in this direction, all right, so mass into acceleration is the cyclic shear stress being applied, right? So into acceleration, so that acceleration we have to find out from the earthquake motion that is occurring in the region, all right? So we have to plot out the cyclic stresses that is developed during the earthquake. So this is the cyclic stresses developed during the earthquake. Then we know that the soil will have a resistance. So the resistance, shear resistance, we have to find out. We have to find out the shear resistance. So what is the peak cyclic shear stress basically to cause liquefaction in n numbers of cycle? All right, so then we will plot that. So whenever the peak cyclic stress needed to cause liquefaction, that is the cyclic resistance of the soil, is less than the cyclic shear stress applied on the soil due to the earthquake motion, then the soil is susceptible to liquefaction. So we have this zone of liquefaction. So how to evaluate that? All right, we will do that in the next class. Okay, so thank you for today.